Good afternoon. Okay. So we've been doing implicit differentiation. So today, let's make a question. We'll practice implicit differentiation in this question. So here, this is a function that has x and y, and the y has a cube power. Function that has a cube power in one variable, we normally don't have a calculation formula. If it's degree 1 or degree 2, we will have a formula for calculation. So this one is difficult to solve y by itself. So it's very common for us to just go ahead and differentiate both sides of the equation in order to find the derivative. So we don't have to determine the formula for y. We wish to find a formula for y prime. Dy dx or y prime is basically the same thing. Try to do it yourself, and then if we have different answers. All right, so this is our formula. With that formula, we're going to find the derivative of both sides of the equation. Differentiate both sides of the equation. That's the implicit differentiation. Sitting behind it is to find the derivative. Right. So you can see the first term is x cubed. The derivative of x cubed is 3x squared. Right, derivative of the second one, it's going to be a little hard to do. We have to do product rule. So I'm writing there, I write parentheses x, y, parentheses prime. Which indicating this is something we're going to spend a little time in. We're not doing it right now. Just write out the notation to indicate this needs to be calculated. This needs to be differentiated. After that, we have y cubed. According to power rule, we differentiate a power function. We move the power to the front of the power function. So this has a derivative of 3y squared. And then you have to multiply by prime because it's the y term. Right, so this is for the most part, the differentiation of the left side of the equation, the right side, if you differentiate, it's zero. Derivative of a single number is zero. So this is, we have done the differentiation for x cubed. We've done the differentiation for y cubed. All right, we still yet to calculate the derivative of x times y. So that we have to apply product rule. Let's do it slowly so we don't lose track of the terms. Hope that you're with me. The main goal is to eventually find a formula for y prime. So everything else has to be needed. And right now, we realize the only one that needs to be calculated further is. All right. So this part is what I wanted calculation. So I want to finish calculating the xy prime with product rule. I want to do it slowly. All right. So we will do. So let's use a pair of parentheses. All right. So this most of the part are still the same as last step. All the same except this part. So we're gonna find the derivative of x, just like x prime, and then times y plus. Gonna keep the x and differentiate the y, which then it looks like a y and then prime, but you can just skip the parentheses part. It's just the differentiation. So x times prime. That would be it. But then the derivative of x prime is 1. So this is just 1 times y. 1 times y equal to y. So finally, if we combine everything, it looks like 3x squared minus y plus x y prime plus 3y squared y prime equal to 0. Right, and then I have the parentheses in this place because I need to complete the derivative. This derivative is supposed to be a single term. But once we finish calculation, you need to find out the relation between the term inside and outside of the parentheses. You have to work on remove the parentheses, that you move a little bit, change to the side. Spaces. Maybe you have already finished the calculation. So this is going to be 3x squared. After removing the parentheses is minus y. See, this one has no y prime because we're really only differentiating the x term, and the y term is just play as a coefficient, as a number. This is a summation because of product rule, but with this minus sign outside, it's actually minus x y prime. And make sure you did change the sign as you remove the parentheses. And then we have plus 3y squared and then y prime. This is when all the differentiation is done, and then we realize we have 4 terms on the left. 2 of them do not have y prime. 2 of them has y prime. The one that has no y prime, we have to move it to the right. So we would keep the negative x y prime plus 3y squared y prime on the left. And all the other ones, we have to move it to the right. By moving, we mean we subtract them. So we subtract from both sides of the equation. So you subtract the 3x squared. This is gone. And plus the y. The plus y, they'll cancel the negative y. But then you have to have the plus y. That's what we happen. And the final step is get y prime factored out. That's y prime. Everything else is negative x plus 3y squared. It's other than the y prime part. This can equal to negative 3x squared plus 1. And then one more thing is the division. last step will be the division. That's your final step. Now you have a y prime. The formula for y prime, so y prime, which is that one, will equal to division. So you're going to take the numerator divided by the denominator by the 2, and you have the final answer. Any question? For the most part, I think it's straightforward for the differentiation of x cubed and y cubed, but it's not so straightforward when differentiating x times y. This is the kind of thing that sometimes occur in the question. Even on web work, we have quite a few questions for implicit differentiation. Right. So I hope I give you some idea for the final answers. 14. You don't have your card? Okay. All right, let me find the image. Do you have your phone that takes pictures? I need the card number. Oh, okay. And I can find the card image. You can also find it online yourself. It's or you can take a picture of the image and then use that. Okay. You able to fix the orientation? And I know most of them will take all classes, it's a little hard for them. You can also just leave it on the table in the right orientation. That way it will also change. I think it's a scale. Did you scale? It's doesn't look like a square. It looks like a rectangle. Right. Actually, your brine is too bright, but the scanner can't tell. There's something. You actually have to lower the brightness. Okay, yeah. Okay, any homework questions for yes? 6. Okay, so the question says find the slope. So meaning that we have to find the derivative. After we find the derivative, we have to plug in the number. So the derivative is a formula, but the slope is a number. So yeah. All right. So we got this equation to work with. This is our equation. Well, in order to find the derivative, we have to work with the equation. This equation has denominator and numerator on the. There's a fraction on the right side. Since we have equation is equivalent, so you can change the equation from one format to another format. So even though we have a division in this equation, we can actually multiply both sides of the equation by the denominator to make it less complicated for differentiation. If we're differentiating right now, we're forced to do the quotient rule on the right side. But if we multiply both sides of the equation, that means you try to change the equational format before you take the derivative, so it's easier for differentiation. So multiply both sides by the denominator. Just the type of steps. Multiply by xy plus 8 on both sides of the equation, and that will cancel the denominator on the right, but it will add an extra term on the left. The term on the left is y squared. If you multiply xy plus 8, multiply this way, put it in and then multiply. So that's multiplied to the left, and then your right side will be just x cubed. Right. Are we okay so far? Any questions? So that should be slightly easier than the original format, and because we're gonna do differentiation, but before that, let's multiply out. So you're gonna multiply this with this, the y, multiply this y is gonna be y cubed. So you're gonna have y x times y cubed is attributed. And then this multiply the 8 is y 8 times y squared. This equals x cubed. Right, and then we're going to start differentiating. Because the terms are separated, there's no more parentheses, there's no division. So if we can try to work with the equation, simplify it so you will have less complication when you are trying to find the derivative. They're actually equivalent. It's possible to start out with the first equation. You could just go ahead and find the derivative on left side and right side, but then definitely the right side are going to be a little bit complicated to solve. So we're going to try to remove any parentheses, remove any divisions, so that we have simple equations like this. Now we're going to find the derivative of the left and then derivative of the right, and they should equal. The derivative of the right side is 3x squared. There's no question, that's a power rule. And then we're going to try to find the derivative of the left side. Right. The second term is more straightforward since there are only one variable, which is y. So if you differentiate, you will get plus 16y. You have 2 times 8, which is 16. 2 minus 1, which is power 1. And then this is the y term, y is a function. So according to chain rule, we multiply by prime. That kind of follows normally how we treated a y term, right? The first one is harder. This one, there's 2 variables. There's an x and there's a y. Y is a function. Y naturally also have x. So you have 2 functions multiplied, and therefore you're gonna have to do product rule. So according to product rule, we're gonna differentiate the x times the y cube, plus this time we're gonna keep the x, and we differentiate the y cube. All right, I'm writing it this way so it's clear that we're doing product rule and there's further calculation necessary. So next up, I'm going to finish all the one that we put prime notation on. X prime is derivative of x, which is 1. 1 times y cubed is just going to be y cubed. The first term, after we combine the 1 times the 1 with y cubed is y cubed. The second one, you have to keep the x. That's what we differentiate the y cubed. Derivative of y cubed, if you do it by itself, you have to do power rule. That's 3y squared. But then because y is a function, we have to multiply by prime. That's chain rule. So because of that, we're going to have the same thing here. So multiply 3y squared y prime plus 16y prime, which equals 3x squared. All right, but now we're almost done. But then we have to take a look at all the terms on both sides of the equation. Some terms do not have y prime. Some term has y prime. y prime is a derivative function notation. We have to solve the y prime. So y prime is our target, and all the one that has no y prime, we wish to move it to the right side of the equation. Only keep the one that the y prime. So what we have left is going to be, I have a habit of moving the number. So let's move the number to the front. So that's 3xy squared y prime. That's this term. And then this one was okay. This one we have 16y prime. It becomes the first term, so I start writing a plus sign, which is then equal to 3x squared. The y cube is, it doesn't have y prime, so we minus the y cube on both sides of the equation. The left side, if you minus y cube, is gone. The right side, if you minus y cube, becomes the term. That's what we have so far. We're almost done, and then what we're gonna do last is factor out the y prime, and then you can have 3xy squared plus 16y, there's actually y, 16y, and then multiply by y, which equals 3x squared xy cubed. And after division, the y prime is equal to division between 3x squared minus the y cubed. This is the future. The denominator is 3xy squared plus 16y. So I finished. And then what we're going to have to do, we make x equal to 4, y equal to 2, actually finish calculating it at the number. So you calculate y prime at number 4, 2, which then equals 3 times 4 squared minus 2 cubed divided by 3 times 4 times 2 squared, which is also 4, plus 16 times 2. This is number 3 times 16 is 48. 48 minus 8 is 40. The denominator is 3 times 16 is 48. 48 plus 32. 48 plus 32 is 80. That's interesting. The answer is actually 1/2, at least on my version of it. Okay, so that's this question. I wonder if you have the same number. You have the same number? Same answer?
Yeah.
Okay. I hope that this process makes sense.
Yeah. I was trying to do the quotient thing development, because that's probably what it wants me to do. I don't know why I work with that.
Yeah, if we try to just go ahead and find the derivative, this side we're gonna have xy plus 8 squared in the denominator, and we're sure we'll have a lot of terms. I feel like that's gonna be most of my both side equations. Free of the fractions. A fraction as a derivative. That's. Any other questions?
Looking at the practice test, I just have one question about first being four.
Okay, number 4.
Yeah.
That's, you can do a log differentiation, or you can just take the base 7. What was the question?
What?
Did you see the solution?
Yeah, I was.
Was the solution wrong?
No, it was just I was confused.
All right. Let me try to go through this one more time, try to make sense of it. This is the derivative of the exponential function. So, so if you want to find the derivative, realize the overall function, it is a differentiation of the logarithm function. So if you differentiate the outside function, it's a chain rule. So you will have 7 to the negative 6 over x. Right? You're gonna have the same thing because that's what it is whenever you differentiate anything that involves exponential calculation, right? And then you have to multiply the ln of 7 because we don't have base e exponential. We have base 7. So whenever you differentiate anything with other than base, you always have the ln of 7. Are we okay?
Yeah.
And then you have the inside function. This entire thing is the inside function. We have already dealt with the 7. The ln 7 is there. So we're gonna find the derivative of the inside function. So I'm just writing on the notation here. We gotta know the derivative of negative 6 over x. So how do we exactly find this? You can do it inline or you can do it separately over here. If we're differentiating negative 6 over x, right, one of the things you have to do, maybe rewrite it so it looks like a power function. It would be negative 6x to the power of negative 1. So I'm rewriting it so we can actually relate it to a power form. Because whenever you have 1 over x, it equal to, see that part? 1 over is negative 1 power. So this is an x to the negative 1 power. So flipping the 1 over 90 degree to become negative 1. So this is actually the same thing. So if you have 6 over x, which then equal to 6 times x to the power negative. That's essentially when you multiply 6 to the 1 over x. Just try to derive it. And then we're adding a negative sign to it. Add a negative sign to this, so you add a negative sign there. So I'm saying that this is the same thing as this. So we can basically apply power rule when you try to find the derivative. Right, so this is equal to the power is negative 1 multiplied with negative 6 is 6. And then the power has to be minus 1. Negative 1 minus 1 is negative 2. So this is negative 2 as a power, right? Power rule. Are we okay? Any questions? Okay, so that's really my way trying to explain how we get this derivative. Find power rule. And whenever the power is negative, it's actually division. So this is actually equal to 6 over x squared. I'm trying to connect the original function is negative 6 over x. Now the derivative function becomes 6 over x squared. So lower the power. See, that's the negative 1, and this is power negative 2. All differentiation function apply to a differentiation function of a polynomial, lower the power. So anyway, this is the derivative. I'm just trying to rewrite. It's going to be 7 negative 6 over x times ln 7, and then times 6 over x squared. And that's every component of the differentiation. This is applying chain rule. I applied chain rule one time.
Yeah.
Any questions? You can compare that with my solution.
Your solution is the same.
It's the same. Okay. Question. Yeah. So that part was. I didn't really spend that much time explaining. I mean, if you want to know what's that one, yeah. So this is the process for that. From here to here, that's the process. Any other questions? Our test is scheduled for next Thursday, so we have a little over 1 week to prepare for test 2. Test 2 should be over the entire chapter 2. We're almost done with chapter 2. Yes.
Are you going to reopen the other sections?
Yeah, I am going to. all the chapter 2 homework. So we're trying to prepare for test 2, and it's a good time to study or practice. If you haven't finished all of them, it's time to work them out as practice. Any other questions? So today I want to finish one more thing. That is section 7. The entire chapter 2 has 7 sections. So I should finish one more section. That way we have enough time this week to get all the practice in. Try to go over a little bit about 2.7. And what is 2.7 exactly? It's try to find the derivative of the inverse function. One of the special inverse function is inverse trig, and we will have it on our calculator. We have sine inverse, cosine inverse, tangent inverse. So obviously we should be able to find the sum of the common derivative for the inverse trig. And with that, we have to find a little about the inverse function before we talk about the derivative of the inverse function. So what's the inverse? All right, so for example, we had y equal to sine, and you know the derivative of y equal to sine? Cosine function. So, cosine and cosine, they do have derivative. Some function has derivative, some. All right, so then, yes, and we talked about that. Sometimes you want to try to calculate a derivative. Basically, you're calculating the slope. But sometimes the function does not have slope, so which is a direction. So, for example, the absolute value function, at 0, it does not have derivative, and some function does not have derivative at any point. So to have the derivative of the function, it really has to be a smooth function, where you can actually find a direction at every point. That it has to be a smooth function. Now, other than derivative function, we're going to talk about inverse function. Some functions have inverse, some functions do not have the inverse. To have the inverse function, the function itself has to be 1-to-1. For example, one of the common examples that has inverse is the logarithm and exponential function. Now, for example, y equal e to the x, most of the exponential function behave similar to it. It looks like this. So what's the inverse? The inverse of y equal e to the x is y equal ln of x. And how does it behave? See, this point is 0, 1, because e to the 0 equal 1, 0, 1. Right, but logarithm ln 1 equal to 0. So logarithm the x equal to 1, the y equal to 0. So it has a 1, 0. So right here you have 1, 0. So to graph the function, this function occupies the entire upper part of the e to the x. It occupies the positive y value. So the inverse replace x by y. So switch this to your ln. So it only occupies the positive x. This graph only occupies the positive y. This only occupies the positive x. That's why the logarithm does this, right? And inverse function and the original function, they are symmetric about this line. This is a line y equal to x. Because the relation between the inverse is when you input become output, output become input. That's really used. We'll switch x and y to get the inverse. This is the relation between the inverse and the original function. The idea is going to be very persistent in any question related to inverse. All right. So first we got to understand the relation between the function and the inverse function. So we're going to review a little bit about inverse function relation. So if you get y equal to fx being a function, and suppose it is 1-to-1. One of the common functions that's not 1-to-1 is the square function, like y equal to x squared, right? It's not 1-to-1 because 1 squared is 1, negative 1 squared is also 1. So then for 1 as the output, there's 2 inputs to match it, and therefore it's not 1-to-1. By 1-to-1, we mean every input has only 1 output, and every output has only 1 input. That's 1-to-1. So that's actually a really a special requirement. Many functions do not satisfy that requirement. But suppose the function is 1-to-1, we're able to find the inverse. we give the inverse a special notation. It says f to the power -1. That's the notation for the f inverse. So we kind of just sometimes switch the two. For example, when you see f of a equal b, then f of the inverse of b would be a. One of the understanding is that the f and f inverse, they will cancel each other out if they're joined together right next to each other. So for example, if you have f of a equal b, all right, and then you have the f inverse acted on the left and acted on the right is, so if you have f inverse here and then f inverse here, these two, since you cancel each other out, the identity function, you get rid of each other, then this is a equal f inverse of b. I'm trying to explain that notation. Okay, so I'm trying to explain. Sometimes you see we enter the f inverse into a discussion or into a process. Sometimes will be what's going on with that inverse, how it affects the equation. Just think of it from the equation perspective. Think about using f inverse on both sides of the equation, and you kind of say this two cancel each other out. Get that part. All right. So suppose we use a new notation for the f inverse, and then the notation is slightly shorter. So instead of have f inverse of f, we have f of g. Then just like the f inverse cancels f, then if g equal to the f inverse, then the g will cancel the f. All right. So when they are together, they get rid of each other. So that. All right, so that's a couple of things. So fgx equal to x, gfx also equal to x. That is the f and f inverse will be like equal to when we're not there. Then f inverse also cancels f. So one way or the other, the identity function. I can explain. And visually, they'll look like one like symmetrical point. Just like on the graph, I have 0, 1. Over here, you have 1, 0. It's symmetrical about the line y equal to x. All right. I did draw the graph before for the exponential function. This is another example. What we have here, the one that's solid line is the original function f, and then over here, the gray line, the gray curve is the inverse. All right, so you can see they're symmetrical about the y equal to x. And so one point on the line goes 1.5, and then the inverse is 1.5 and 1. So they have point that matches each other in the inverse relation. Input become output, output become input. And that's relation inverse. All right, let's see how we find the derivative of the inverse function. We actually go by the, what do you call it? The implicit differentiation. So 2.6, 2.7 is being introduced right after 2.6. So many things that we do in 2.6 is now relatable to 2.7. Let's look at this example. So how do we find the inverse? This process, you might have to do it individually by itself rather than do that on this notation. This is just explaining some of the logic. Say you got an inverse function such as sine inverse, cosine inverse. This is our inverse function. If you do have an inverse function. All right, with that inverse, you want to find the derivative. But before you find the derivative, you want to revert it back to a more relatable process. So we will use f on both sides of the equation. So have f on this, and then have f on this. So you're going to have f on left and right of the equation. And that way the f on the left, f on the right will cancel the f inverse. So this becomes the x, and this becomes f of y. All right, so why do we do this? Because very likely you know the derivative for f, but you don't know the derivative for f inverse, and you are trying to find the derivative for f inverse. Kind of like we know the derivative of sine, we do not know the derivative of sine inverse. So what do? maybe we can use a derivative from sine to help this when you try to calculate the inverse. And that's what we're doing right now. After we find this, suppose we have derivative now. We're going to try to do inverse differentiation on both side equation. This is kind of the process. So we're going to try to find the derivative of the left and derivative of the right. So we're going to find derivative of this and derivative of this. We're doing this. All right, if you are differentiating the right side, derivative of x actually equal to 1. If you are finding derivative on the left, this is like a hypothetical. Hypothetically speaking, we have the derivative for f, which is f prime of y. Now, the y is a function, so this is differentiating a y term. You have to multiply by y prime. That's what happens if y is a function. All right, so now we want to find the y prime. This is multiplication. So in order to get y prime by itself, we're going to do division. So y prime is equal to 1 over f prime of y. So this carries the idea that if you're able to find the derivative of the original function, the derivative of the inverse is actually a reciprocal. 1 over. Does that make sense? The reciprocal. And we can relate it to using the graph that we already have here. And just to say that relation of inverse. Without this part, let's see how. You can see some of the slope. So for example, here, the slope equal to 1 and 1 over 1 still equal to 1. So you can think of it as m equal to 1. So this m also equal to 1 because it's 1 over 1, so 1. But you can see over here, this one, slope is faster. You can think, suppose it's m equal to 4. What about this point? This way. So the m actually equal to 1 over 4. Trying to make sense of that relation, saying that the derivative of the inverse, which is a y, like y equal to the inverse. The derivative of the inverse actually is 1 over the derivative of the original value. Okay, any question? So that's what we are trying to go over, and with actual example, maybe we'll have a better understanding of it. So this is the number one thing that we learned is that derivative of the inverse function equal to 1 over the derivative of the original function. Any question to that matching point? Yes, let's look at a couple of examples. These are the derivative of all the inverse trig, and we should do the one for the sine. Maybe that way we can have a better understanding. All right, so for example, let's say we try to find the derivative of y equal to sine inverse. Sine inverse all of x. Okay, so number one, we gotta understand the meaning of sine inverse. Sine inverse is an angle that has a sine value. So basically, the sine inverse of x equal to 1 means that if you use sine function on both sides, means that sine of y will equal to, see, sine of the left equal to sine of the right. So on the sine of the right is sine of sine inverse, which equals x. Right? This is equivalent. So whenever you have an inverse function, you have the original function between the inverse and the original. Right? Before it was y equal to f inverse, and that means that fy equal to x. Now, if you have sine inverse, this is the same relation. So once you revert it back to the original notation, you realize this thing. The y is actually an angle. So yeah, this triangle here. The y is an angle. Sine of this angle equal to x. Assuming this is a 1. Let's try to make it easy. Then the sine equal to opposite over hypotenuse. Hypotenuse equal to 1. This must be the x. Right? So this way, the sine y if y is an angle, would equal to the hypotenuse or the hypotenuse. That's trigonometry in triangle. Opposite over the hypotenuse. And the way I draw it, and I'm forcing the hypotenuse to equal to 1. So this is 1, this is the x. That way the sine y equal to x. So then the x will be a part of the picture. I'm doing this because eventually I need to figure out a formula for the inverse trick. So this is helpful to understand which one is the angle, which one is the length. This is a length 1, this is a length x, this is the angle y. Angle is a relation between the initial side and terminal side, right? Angle is not a length. Angle represents relation between two rays, but it's a different measure compared to a length and distance. Any question? The basic thing that trigonometry does is to use ratio between the lengths to represent, relate to an angle. So what we're gonna do is that once we realize this, we are able to start differentiating both side equation. So from here, you're gonna find derivative of the left and derivative of the right. So originally it was sine y equal to x. We're gonna find the derivative of the left and then also find the derivative of the right. If you find the derivative, you see we're doing this over and over. Hopefully with enough scenario, we'll start getting the pattern. Derivative of the x equal to 1. Derivative of sine y equal to cosine y. But then y is the functions, you're gonna have to multiply that with y prime. This is because of chain rule. All right, and again, we're hoping to find this function's derivative, right? We're hoping to find the y prime. The y prime is a derivative of the inverse trig, even though we reverted back to the original meaning. Because we have derivative of sine, we don't have derivative of sine inverse. That's why we write it into sine. That way we have a formula for the differentiation. So from following this, we have y prime, which equal to 1 over cosine y. 1 over cosine y. But there's this thing, when you try to find derivative of a function, you're supposed to have x value as your derivative, not having a y there. So this is like whenever you use the implicit differentiation, you have y as part of the derivative. Implicit differentiation, you have to revert back to the original variable. So what do? We have to understand what's cosine y exactly. So back to this picture we're drawing. Sine y is opposite of hypotenuse, which is x over x. So what's cosine y? Cosine y is adjacent side over the hypotenuse. Now the hypotenuse equal to 1. So what's the adjacent? Adjacent side is this side. According to Pythagorean theorem, we have x squared, calling that a. X squared plus a squared equal to 1 squared, which equal to 1. So then the a squared equal to 1 minus x squared. So then the a, which is the adjacent side, equal to 1. Square root of 1 minus x squared. So this is actually square root of 1 minus x squared divided by 1, which then equal to 1 minus x squared. That is the cosine y represented by the x value. So this is equal to 1 over root of 1 minus x squared. So it does involve a little bit of study of the triangular relation between angle and their trig value. So that's the derivative of sine inverse. And that's the source of this formula. The first formula is derivative of sine inverse is 1 over square root of 1 minus x squared. Derivative of cosine inverse, they're very similar. But once again, whenever you have a co-function differentiation, you get that negative sign. So that was positive 1 over root of 1 minus x squared. This is negative 1 over root of 1 minus x squared. Another interesting thing is that we are differentiating a trigonometry function, universal trigonometry function, but we don't have any trig in the answer. That's something that's kind of funny because not only when you differentiate trig function, your answer is not a trig function, but inverse trig is different. And that also could be one other thing is that this is inverse function are not defined for the entire tree. The inverse function is artificially only defined for a small portion of the number, right? Remember, all the inverse strings are defined only for a special x value. We're not defining it for all x values, obviously. This rules require the x squared to be less than 1. So only x between -1 and +1. We will have an inverse, and any number other than that is not possible to find. Other than that, we had a tangent inverse, and this is something that we hope that we'll remember. Derivative derivative of tangent inverse is 1 over 1 plus x squared, and derivative of cotangent inverse is -1 over x squared. Again, whenever you have differentiation of a cofunction, you always have a negative sign. There is a function, cofunction. And these two also is like secant and cosecant, there's negative. Other than that, they're almost the same. Any questions?
Could you go back a slide?
Okay.
I'm sorry, the one where you showed the work for the derivative cosine.
The actual process is actually here. From here, you go here and find the derivative, and once you implicit differentiation, you get this. And that is the fundamental reason why we want to revert back to x. This is analyzing the triangle, so we would know y equals some y. So we do the minus squared. It has a little separate here.
That's good. Of the, you can inverse, what would the absolute value? Does that mean anything, or is it just meant that it can be positive or negative?
It means that we have to have the x have, yeah. Yeah, I went over the sine inverse. We can run over the secant inverse together. Let's try it. Is that okay? Maybe we should go and do this one. No. Let's try to prove this. So it's the same process. You still have to define the y's again. Let's say if y equal to secant inverse of x, and so revert it back to the secant function. That means secant of y would equal to x, right? And then we would find the derivative of both side equation. Derivative of the right equal to 1. Derivative of the left, that's where we have the multiplication. Derivative of the right equal to 1. Derivative of the secant is secant times tangent, right? Right?
Yeah.
So derivative of secant is secant y times tangent y, and then times y prime. And that's the reason we have a multiplication. So y prime is equal to 1 over secant of y times tangent of y. All right, and then that kind of explains the multiplication. See the multiplication there. All right, so we're going to try to look at the relation. We have secant of y equal to x, so that cosine of y would equal to 1 over x, because secant and cosine are reciprocal. What I'm trying to do is put everything into a triangle. So again, I'm drawing a triangle. The y is the angle, so this is the inside of the trick, y is the angle. The cosine is 1 over x. Cosine is supposed to equal to adjacent over the hypotenuse. So then the hypotenuse, this is x, and the adjacent is 1. This is 1. So I'm trying to label the triangle according to how the cosine is being defined. Okay, so far. So then that means that so what's up with the absolute value? I can understand the secant here. So it's 1 over, see the secant equal to x, so then this secant is the x. So the tangent, let me go through the rest. The tangent of the y would be a tangent of the angle. Now tangent is opposites over adjacent. Opposite over adjacent. Now the adjacent is 1. And the question will be, what was the opposite? Let me call the opposite, call that b. Right, so then the 1 squared plus b squared equal to x squared. So then the b squared equal to x squared. That's 1 minus 1. Right, so the b as a length is square root of x squared minus 1. So this is b is the opposite side. So this is root of x squared minus 1. So this explains that the tangent of the angle equals x squared minus 1. So that's time x squared minus 1. Why does it have to have a absolute value sign? All right, so far, are we okay so far with, we kind of explained the whole structure, right? It's 1 over, that was supposed to be the secant, and that was supposed to be the tangent of the angle.
I'm not sure whether it's just trying to denote that it could be negative or positive, or like there has to be positive.
For secant inverse, this is an angle that's, why does it have to be positive? I mean, with the absolute value sign, we're forcing the entire value to be positive.
Yeah.
It could be that the function itself only have positive, so we look at the function itself. Don't work with secant inverse as much. Because we normally do work with sine inverse, cosine inverse, and secant inverse is one that's not very common. All right, so you kind of see that this function only have increasing behavior. So it's like always this way, only when the curve goes this way, it has negative slope. So any point on this function, it doesn't have a decreasing slope. The entire function was always increasing. So we're trying to make it positive by taking the absolute value sign. That's as far as I can.
Okay. Well, cosecant would also be the same.
The cosecant would always be negative, what it looks like.
Oh.
And then this is forcing it to be always negative because the root sign is always positive. The absolute value is positive. Put a negative sign before it, that's guaranteed to be negative. To have a negative slope means the function would be decreasing.
So it would always have negative.
Yes, so this is a cosecant inverse. Right, so this is a,
It would always be decreasing.
yeah, this is a cosecant inverse. It will always be decreasing.
Okay.
Yeah. For any given x value, it would always be decreasing. That kind of goes through the first two examples. Sine and cosine inverse are similar, and secant inverse and cosecant are similar. Tangent inverse and cotangent are very similar. I guess we should also talk about the tangent inverse derivative because that's almost the one that if we have to remember some of the trig inverse differentiation, that would be sine inverse, cosine inverse, and tangent inverse. All the other three are not very common. So suppose we have tangent inverse, we want to know the derivative for the function. So y equal tangent inverse of x, and what is y prime? That will be the question. All right, to answer the question, we will revert it back to the tangent function itself, and that will be a tangent of y equal to x. This is apply tangent to both side equation. If you apply tangent to the right side, it becomes x. If you apply tangent to the left side, it becomes tangent y. And then we can find the derivative. Differentiate the right side and differentiate the left side. You differentiate the right side is 1. You differentiate the left side, derivative of tangent is secant squared. Secant square of y, that's a y term because of chain rule, you multiply y prime, and that way the y prime is 1 over, so we always do this, 1 over whatever the derivative is secant square of y. And then again, the derivative of a function, we have the x variable, we were supposed to have an x variable, so we try to convert it to an x following 1 for the secant square, and then we're back to the original triangle. Let's try to draw the triangle for tangent y equal to x. So right here, the triangle, the y is a angle. Tangent is supposed to be opposite over adjacent. So this is the opposite, which is x. The adjacent has to be 1. It's x over 1, x, and that will be it. And then the hypotenuse, which would be root of x squared plus y squared plus 1 squared, squared plus 1. So that's the triangle. And we're going to find out how to represent the secant y. All right, to represent secant y, you got to represent cosine of the angle. So cosine y is supposed to be adjacent over hypotenuse. That's 1 over the hypotenuse. Hypotenuse is root of x squared plus 1. That's a cosine y. Therefore, the secant y would be the reciprocal. So secant y is actually just hypotenuse over adjacent, which is root of x squared plus 1. That's secant y. So if you have secant square y, you have 1 over x squared plus 1. And that proves the derivative. So derivative of tangent inverse is 1 over x squared plus 1. That's the trig differentiation. Any question? So this goes through this one through all the process of explaining why is the derivative of tangent inverse 1 over x squared plus 1. So that's another example. You started with a inverse trig, and you end up having something that has no relation to trigonometry whatsoever. It's actually a rational function. And that's something that's not very common. Most of the scenario that we had so far for differentiation, if you differentiate a polynomial, the derivative is a polynomial with lower power. You differentiate a trig function, sine derivative is cosine, cosine is negative sine, derivative tangent is secant squared, and then so on. So most of the time, derivative say trig function is another trig function. So derivative exponential function has exponential function, derivative logarithm, that's something that's totally different, right? The logarithm is 1 over. But we should try to think about some of the common patterns. That way when you apply it, you will see the differences and similarity. All right. So that's a summary of all the trig, inverse trig differentiation. And all right, one of the scenario is to find the derivative of logarithm. And we know it's 1 over x, right? Or we know it's 1 over x from before, but now we can actually prove it. I went over this yesterday before the class is done. Then I did mention the inverse. Okay, so once again, if you have y equal to ln of x, and by the inverse, so we have e to the y equal to x. Because the inverse of ln is e, so you have e of the left, which equal to e of the right. And then that's why e to the y equal to x. E and ln is inverse function of each other, so we cancel. Now we can find the derivative with e to the y equal to x. We'll find the derivative of the right, and we'll also find the derivative of the left. After we've done that, the derivative of x equal to 1. Derivative of e to the y is e to the y times y prime. That's because exponential function derivative would always be itself. but then we gotta multiply the derivative of the inside function. So the y prime is now equal to 1 over e to the y. And then again, whenever we try to find the derivative, we wish to represent it with the original variable. So you don't want to have y prime equal to a y formula. You want a y prime to have the x formula. So we're going to try to study our process to find out exactly what was equal to y. Halfway there is a u of y equal to x. So that is, because of that, we have that this is equal to 1 over x. And that proves that the derivative of the logarithm actually equals x. And this is something that we keep mentioning and haven't had a clue for any question. All right, so this is the last question in this file, and let's go through some examples from the homework so we can have some filling. I haven't really assigned it, but before that, let's try to do them. I'll assign it after class. Maybe you want to try it yourself. Let me assign it so you can see it on your side. There should be a different version of it. Is 21st. All right, let me assign this so it's visible on your side. Try the first question. It's normally something my students tend, when they first start working on it, they always have some question because we're not familiar with work with inverses. All right, so when you look at it, you see a polynomial, and this is actually a higher order polynomial. I mean, that's why it's kind of looks strange. All right, and then the question says, for each of the given function, find the derivative f prime of c at a given point c when a equal to f inverse of c. So kind of to look at what does it mean? So c is the input for the inverse. So c is actually represent a y value. I hope that makes sense. Are you okay? This is an inverse. So that you can also look at this. All right, a equal to f inverse of c. So therefore, if you work on f of a would equal to c. That is saying for your function f of x, the a is a x value. The c is supposed to be a y value. Let's be clear with it. Are we okay? Are we okay? Clear. All right. So therefore, this c, this so-called c number should be a y value. That should be equal to something like this. So you have to what you're looking for is 5x plus 9. This is our y. Like y equal to 5x plus 9x to the power 17. And then we wish to have this equal to 14 because the negative 14 is c, and it's the y value. It's the output. It's the input for the inverse. Therefore, it has to be an output for the original function, like inverse of the inverse. Are we okay? So how do we make it negative 14? See, we really wanted negative 14 to equal to 5x plus 9, and then times x to the 17th power. So what should be the x value? And what should be the a value exactly, right? C is a y, a is a x. And the first question is get to know the a, which really is the x. So what kind of x value will give us negative 14 in this calculation? There's an easy number, right? Just think of a simple example. Don't make it too complicated. What should be x? Well, when you look at the coefficient, we got 5, we got 9, we got 14, right? So what should be the x value? 1. 1 will make it positive, so at least we should have a negative, right? Negative 1, right? Negative 1. So if x equal to negative 1, you have 5 times negative 1 plus 9 times negative 1, because negative 1 to the 17th power is still negative 1. So that's going to be negative 14. So number one thing, we have to find the corresponding x value. To find the corresponding, to know that a is an x is very important. Sometimes my students work really hard, but they were trying to find a y value to make the x equal 14 and y equal, but it's y that equal negative 14, x is negative 1. So that's the first step, that is trying to figure out the right match. This is supposed to be negative 1. Once we figure out the right x and y pair, let's think about the derivative. And according to what we just said, we have this, let's try to find the derivative value. Now, according to what we said, the derivative value is supposed to be the reciprocal of the original function. So this is equal to 1 over the derivative of the original. So we're going to plug in f prime, so we're going to plug in the a, right? This was f inverse, this is a y value, but here you're going to play the y for the inverse, but the x for the original. So we were supposed to calculate 1 over f prime of a is negative 1. So you will find the derivative of the original function and calculate it. So what's the derivative of the original function? It's f prime of x or y prime of x. It's equal, derivative 5x is 5, derivative 9, 17x is 9 times 17, and then x to the power 16. That's the derivative. And then we're going to plug in x equal to negative 1. So f prime of negative 1 is equal to 5 plus 9 times 17. And then negative 1 to the 16 power is still 1. So that's pretty much 1. It's negative 1, right, to the 16 power, which equal to 1. And then if it's multiplied by 1, you don't have to multiply. That will be the answer, which goes in the denominator. So you go back, and that will be 1 over, and this is 5 plus 9 times 7. So it's an odd way to think about it, but in this case, you are using the 1 over the derivative of the original function, which is the derivative of the inverse function. Like that relation was quoted in the PowerPoint of this one. This is an inverse derivative. The inverse is 1 over the and we go through the same process for the second question. And you have this function, and we want to have the c, which is y, we're at 11. How can make this equal to 11? So I have to solve for this. And to solve the second question, you're gonna have to figure out what would be appropriate x value. So hopefully this will give you one taste of the inverse differentiation of the inverse function. All right, so basically, as we mentioned, a is equal to f of inverse of c. So then f of a, f of the left equal to f of the right. F cancel the inverse. So we get c. Right, that is saying whatever you are calling c, it was the y value. Whatever you're calling a, it was the x value. So here we have a y value to a 11, and then the y value is equal to x squared minus 15x plus 61. To solve this, we're gonna make it equal to 11. Y gotta be 11. We have to find the x, the a, which really is the x. We're solving for the x. So 11 is equal to x squared minus 15x plus 61. Let me write the 11 on the right side. And that's the equation right now. All right, and then we're going to minus the 11 on both sides of the equation. We then have x squared minus 15x. We minus 11 and minus 11. So this is a plus 15, which equals 0. Now 50 is 5 times 10, that's the 50. And then 5 plus 10 equals 15. So when you add is 15, when you multiply is 50. So x minus 5 times x minus 10 will be the right factoring. And we have two solutions, x equal to 5 and then x equal to 10. But there is this domain, there is this interval saying x has to be higher or equal to 7.5. With that, we can't use this one because 5 is below 7.5. We want things that number that bigger than 7.5. They leave us only one choice. X has to be equal to 10. At least that's on my version. Question. All right. Then again, there's a last question is the derivative for the inverse, which will be 1 over the derivative of the original. What's the derivative of the original? It's f prime of x, which equal to 2x minus 15 this version. And we need to find out what is the value in the x equal to 10. So f prime of 10 is the derivative of the original function. That's 2 times 10 minus 15, which is 5. So that goes in the denominator. The denominator is 5. 1 over 5 is our answer. And that clearly indicating that derivative of the original function is the inverse of the derivative of the inverse. Derivative of the inverse function is the reciprocal of the original. So a reciprocal relation will answer this question after differentiation of the original. So this is it, and this is a 1 over 5. At least on my version of it, it will be it. That'll be for today. It's okay. So try to look at your version and see some relation there. If we are able to figure out this one answer, then the second question might be similar. Should be okay. Basically, there are two type of questions. One type is this type, and the other type is the trig inverse. That will be it for today. That's it. I'll see you tomorrow. Thank you. All right. If you haven't done the quicker question, let me know. Cody, you.
I didn't do it. I also didn't do it yesterday.
Okay.
I was here though.
Yeah, I know.
Okay.
So this is a quicker question.
I was here though.
The answer was C. We did the inverse differentiation.
Hopefully that's better. Bro, I love that. Man City plays that in Big Six. They only lost one game.
Somehow it was recorded.
But the point is that like for literally only they played 2 other people and they won 3 games. How was that?
So that's the private thing, right? For everybody sends us C, so I think it's pretty good. Fine. See you tomorrow.